Hello everyone, today we're going to look at usaco-training cow tours. Okay, so in this problem we're given n pastures, which each pasture is represented as a letter and has a unique position on the coordinate field. So as you can see, cow pasture A is located at point 1010, cow pasture B is located at point 1510, cow pasture C is located at point 2010, and pasture D is located at the point 1515, and pasture E is located at the point 2015. Okay. So then we can define the distance from a pasture to another pasture as like the direct distance. So for example, you can see that the distance between A and B is going to be 5. Okay. And then our diameter of the field is basically the largest path from one pasture to another pasture. So as you can see, you know that from A to E, the diameter is going to be the greatest, since from A to E, your minimum way to do that would to be going from A to B and then B to E, and then the sum of this distance would be your diameter. Okay, so what we want to do is that we basically we're given an adjacency list where row I and column J means that if there is an edge connecting I and J. So for this example, you can see that A and B are connected because row 1 and column 2 has a value of 1. So then, if this is 1, then it means that there can be a valid path over here. And let's look at AD. So you can see that over here it's 0. So you can see that there's no path from A to D. Okay, so some pastures may not be connected. So we're going to create a new path. So for example, we could create a path between A and D, or we could create a path between A and C. And then we're going to, as you can see, we're supposed to connect two pastures. So the new combined field would have the smallest diameter possible. Okay. So basically, as you can see here, we're given n pastures. Pasture A is this, pasture B, and then here's our adjacency list. Okay. So then, okay, so we're going to print the diameter of the newly joined pastures. Okay, so here you have C and G. So it looks like we're going to connect C and G. So you can see over here, we actually don't have C and G. Okay, so if we connect C and G, okay, so basically this C would be connected to here. So 2010 would be connected to 2510. Okay. So then the diameter of this result would be 22.071. Okay. So since we know the coordinates, basically we can have another adjacency matrix representing the distance between two nodes. So we can call ADJ of pasture 1, pasture 2 equals the minimum distance from I to J. Okay, so you know that we read in an original adjacency matrix, so we have basically it would be 1 or 0. So then, for example, if the distance to itself or if there was in the path, let's just say in the sample we have a path from A to B, you can basically set, for example, ADJ of A of B to the distance between these two nodes, so distance of A of B. But if there is no path, then our ADJ of P1, P2 would be equal to infinite. Okay, so basically, after we do this process, the pastures that have a path connecting to them would have a specific distance, and the rest would be infinite. So what we can do next is we can use Floyd-Warshall's shortest path algorithm to expand this graph. So, okay, so next we're going to apply Floyd-Warshall. So what this does, algorithm. Okay, so what this does is that in O of n cubed, this can basically create all the shortest paths possible, and it would just evaluate the matrix. Because, as you can see, the original shortest path between, let's just say there's a path between A and B, okay, but then there's also a path between A and C, and then C and B. So then you might also want to take this path because this actually might be the shorter distance one. So then Floyd-Warshall would be for each, okay, for let's just say K, it would be from 1 to N. And then for I, again, it would be from 1 to N. For J, again, it would be 1 to N. So then ADJ, IJ will be equal to the min of this, the original one, and basically what I said over here. So basically over here, this would actually be I to K will be created into K and J. So because using these two paths, you would create a path from I to J. So then it would be min this and ADJ I K plus ADJ K J. Okay, so now after we evaluated this matrix, we're going to try to find the answer. Okay, so what we can do first is that we can find the diameter of this graph without adding a new edge. Okay, so let's just say we're going to. So what we can do is that for each pasture, we're going to try to find the pasture that is the farthest away from it. And since basically our diameter would be the longest path, it would be guaranteed that we would find our diameter if we just take the maximum of all the distances. So basically, again, we loop through all the other pastures, and our diameter, since you want the maximum one, it would be max this and ADJ of IJ. And this is only if there's a path from I to J. So if path I. Okay. So then what we want to do after this, 1 second, actually expand this. Okay. Okay, so here. So after this, we know our original diameter. So now we're going to simply try to add a new diameter. Okay. So we can do, again, we can loop through, we can loop through all possible pairs of pastures to add. So for I in range, n for j in range n. Basically, if there wasn't an edge from I to j, or if it's unable to reach I from j. So then basically if a dj of I j is equal to infinite, then we're going to try to add an edge. So what we can do is that then our resulting diameter would be equal to the maximum dist of I plus the distance from I to j plus the maximum distance of j. Okay, so our max dist of I is basically what we calculated over here, but we can actually say that max dist of I will be equal to max this and the distance. So it would be ADJ IJ. Okay. So then now we have our new possible diameter, and our answer would just be the maximum of what we calculated over here and what we calculated over here. Okay. So this problem is Kaltor's. Okay. So let's include. Okay. Okay. So we're going to read an integer n at first. So we have int n. Okay. Let's actually make this a global variable so we can read this. Okay. So now we're going to read in the x and y coordinates. So we know that our maximum n is or we can actually just use max n. It would be equal to 150. So then you would have 150 here. So we can basically for each pasture we're going to read. Okay, so we have our x coordinate and our y coordinate. So for each pasture we're going to read the values for this. So we're going to have two integers, x of I and y of I. Okay. So now we're going to read in the adjacency matrix. So what we can do is that we can have a character string. Let's call this s. Okay. So over here we're going to read in n lines. Okay. So then we're going to read a string. This is s. Okay. So now we're going to expect n characters of input. So we're going to loop through each of them respectively. Okay. So if there's a path between them, so if s of j is equal to 1, then we're going to basically update the distance. Okay, so then what we can do is that we can have our adjacency matrix. And since we actually want this as a floating point integer, we can actually use a long double here. So we can actually using LD equal to long double. Okay, and actually I'm just going to switch to CN and Cout. So instead of using scanf, since it's easier to use CN. So CNN for here will be to CN x of I, y of I. And here, actually we have to include the namespace. Okay, so instead of having a string or having a character array, we're going to have a string. So here will be CNS. Okay. So what we can do now is that we're going to because if there is a path between them, then we're going to set the adjacency value to that. So we have long double adj of max n, again another max n. So if there is this, then our adj of ij will be equal to the distance from I to j. So we can have a function, so it'll be long double dist into I into j. Okay, so we can have our x difference, so it'd be equal to x of I. Dx would be equal to x of I minus x of j, and again you would have your y distance as well. Okay, so then you would just return dx times dx plus dy times dy. Okay, so otherwise distance, or adj actually, of ij would be equal to infinite. So let's actually have an infinite, so infinite will be equal to 1e18, or actually 1e9. Okay, so then this would be equal to infinite. Okay, so another case is that if this is the same pasture, then we're always going to, since you're basically staying, then so if I is equal to j, then your adj ij will be equal to 0. That's just by default. Okay, so now we're going to apply for Floyd-Warshall to this graph. So then for int k and for int I and for int j, distance of ij will be equal to min distance of ij, distance of ik plus distance of kj. Okay. So now after this, we're going to calculate the diameters. So what we can do is that again we can have a max dam, which means the max diameter. So LD max dam, or diameter, of each node. We can actually call this max distance. So from this specific node, the distance from this pasture, or the maximum distance to another pasture. So we're going to loop through each pasture. Okay. So we're going to calculate the maximum diameter for this. So for int I equals j, actually 1 second. Okay. So what we're going to do is that we're going to loop through each of the other pastures. Okay. So originally, since you want the maximum, max dist of I will be equal to -1. Okay, so over here, your max dist I would be equal to the max of your current max dist and your distance of I and j. So now you have your maximum distance. So now we're going to try to first simulate adding an edge between two unconnected nodes, with one of the endpoints being I. So then, again, for each, actually it would be a bit less than I. Okay, so since you want your answer to be as minimum as possible, originally it would be equal to infinite. So over here, your answer will be equal to the minimum of your answer, and basically what we want to check first is that if there is no path connecting these two nodes. So if dij is not equal to infinite, or actually it should be adj, my bad. If it's not equal to infinite, then it means that it's already reachable, so you should not add an edge. So over here you should just do continue. Otherwise, it would be equal to the max dist of I plus the distance from I to j plus the max dist j. Okay. So now, after this, we're going to try to compute for the other diameters as well. So then for int I equals 0, your answer will be equal to max, your answer, and your max dist. So this is basically without adding an edge, and this is with this line is computing if you're adding an edge. So at the end, you would just print. Okay, since we actually have to print it in with 6 decimal spaces, we can use IO-manip, so we can manipulate the input and output. So it would be fixed, then it would be set precision, since we want 6 decimal places, then we want to print out answer. Okay, so if this works, let's actually run it. This is actually usaco-training, training, and this is tours, and let's run main. Let me get the input. Alright, it's running. Okay, so we do have some error. Okay, so actually over here there should be ADJ, since we actually aren't using dist, we are actually using ADJ here. So then, since this is actually our function, not our like array or matrix actually. Okay, let's actually run it again. Okay, let me actually just format my code. Okay, oops, okay, whatever. Okay, so we actually are we're actually printing infinite, which I believe is up there. So I think max dist will be equal to -1, and for each of these, okay, so looks good. So if I equals to j, then ADJ IJ would be equal to 0. So each time it would be min IK and then KJ. Okay, so looping through, the max dist would be equal to the max. Okay, so what we're actually missing here is that if there is no path from I to j, then it means that ADJ IJ would be equal to an infinite value. So if we actually max it over here, then it would then max dist would be infinite, which is not what we want. So if ADJ IJ is equal to infinite, then we can continue. Okay, so 125, and that again does not seem correct. So let's actually debug more. So so we're just looping through all pairs over here, and we're going to try to add these. Okay. Let's look at, okay, so I think we actually are missing something here. So I actually calculated the distance wrong, because the distance is actually the difference in x squared plus the distance in y squared, and then you have to take the square root of this. Okay, so again, submitted it. Okay, it's compiling. Okay. It's still running. Okay, 22.07. So that looks good. I'm just going to submit it. So let's actually reopen. This problem is Caltor. Okay, and we're writing to Is that out, right? std out. Okay, so let's actually submit it. This is Caltor, and this language is C++11. Okay, so here's the problem, and yeah, okay. Second, it's loading. Okay, so this is usaco-training Caltors. Okay, here. Okay, so that is right. If you have any questions, feel free to leave them in the comment section below. Bye.